So this video is going to be about induction. What is induction? Induction is a way of proving statements in maths which are true for any natural number. So we prove a statement is true for all n in n. So the natural numbers, remember, are the set 1, 2, 3, etc. This is the set of positive integers. Okay, and so we're going to look at this by means of an example, right? So the example we're going to look at is looking at the sum of 2k minus 1 from k is 1 to n. Okay, so what's this? This is equal to, well, when k is 1, this is 2 times 1 minus 1 is 1, plus when k is 2, this is 2 times 2 is 4, minus 1 is 3. Where k is 3, this is going to be 5. And we can carry on. And the last term is going to be when k is n, so this is 2n minus 1. That's the last term. Okay, so this is equal to the sum, maybe you can recognize, of first n odd numbers. By a number, I mean a natural number, of course. Okay, so we want to work out what this is equal to, and we're going to get some form in terms of n. Okay, and we're going to use induction to prove what this is equal to, and we're going to prove that the formula holds for any n. Okay, so maybe to start with, it's best to look at some examples. So we'll go ahead and do that. It's good to look at some numerical examples just to kind of build intuition. Okay, so if we call this guy Sn, meaning this is S stands for kind of sum, and the n denotes the kind of the number of numbers in the sum. Then if we take n as 1, then S1 is equal to, so that's the sum from k is 1 to 1, 2k minus 1. So basically this is what we had before, where the last term is going to be where n is 1. So where n is 1, it's going to be 2 times 1 minus 1. So in fact we only have one term here, and this is equal to 1. Okay, now we can do the same where n is 2. We can get S2 is equal to the first two terms. So this is, it's going to be 1 this guy plus 3 this guy. So this is 1 plus 3 is equal to 4. We can carry on. N is 3. We have S3 is equal to 1 plus 3 plus 5. This is 9. And in fact, we can continue and get S4. We'll do this as the last one. S4 is equal to, so the odd number after 5 is going to be 7. So we got 1 plus 3 is 4, plus 5 is 9, plus 7 is going to be 16. Okay, so maybe you've noticed now that these are not random numbers. So these are in fact the square numbers. So this is 1 squared. This is 2 squared. This is 3 squared. This is 4 squared. This looks interesting. So it looks like, I guess we've got this hypothesis now. That's right, hypothesis. So we've looked at some numerical examples, and now we've got a hypothesis. I think that maybe Sn is equal to n squared, right? Because here we have n is 1, we have S1 is equal to 1 squared. Here we have n is 2, and we have S2 is equal to 2 squared is 4, and this seems to be holding. So what we're going to do is, we're going to work with this hypothesis and see if we can prove that it's true. And what we're going to use is, we're going to use induction. Okay, so let's write out our statement. So our claim is this. Our claim is that Sn, which by definition is equal to the sum from k is 1 to n of 2k minus 1. And we're going to claim that this is equal to n squared. Okay. So now we're going to use induction. So the first step of induction is called the base case. And we've actually already done this. So the base case is like, okay, let's look at the first value. So in this case, n is 1. And let's test if it's true. Okay. And we already tested that above, if we remember right here, S1 is equal to 1, which is 1 squared, right? So base case, S1 is equal to 1 squared, tick, okay. So we know that it holds for one case. Now we've got to do what's called the inductive step, which is a little bit more complicated. So we've got the inductive step now. And what we do for the inductive step is we assume that it's true for some random integer n, capital N, and then we're going to show that this implies, so by making this assumption, it implies that it's true for the case n is n plus 1. Okay, so this is what induction is. These are the kind of two steps we have to go through with induction. And the idea is, then maybe you can imagine, if it's true for n is 1, and we know this kind of inductive step holds, then what we do is we can take big N to be 1, and then having assumed that, we've shown that that implies it's true for n is 1 plus 1, which is 2. So n is 1, true, implies n is 2 is true. Now we take capital N to be 2, and this implies it's true for n is 3. So this implies n is 3 true. And you can see that this goes on and on and on, and that we can show that it's true for any n, right? And it can be anything we like as long as it's in the natural numbers, right? As long as it's a whole positive number. So this is the idea of induction, and we're going to use this to prove this statement. So we've already done the base case right here. N is 1, S1 is 1 squared. So now we're going to do the inductive step. So let's go over here and have a look at the inductive step. So inductive step. Okay, so we're now going to assume that Sn, which by definition is equal to the sum from k is 1 to n of 2k minus 1, we're going to assume that this is equal to n squared. And we want to show, so the claim is that Sn plus 1 is equal to n plus 1 squared. So let's have a look at what we can do with this. So Sn plus 1, by definition, when we have the colons here, this means, and followed by the equals, this means by definition, is equal to the sum from k is 1 to n of 2k minus 1. So this is like 1 plus 3 plus 5 plus all the way to, sorry, this should be n plus 1. So the last term is going to be well, let's look at the second to last term. So the second to last term is going to be where k is n. So this is going to be 2n minus 1. And then the last term is going to be 2 times n plus 1 is 2n plus 2, and then minus 1 is 2n plus 1. Okay. And now the thing to notice is that this bit here, the sum up until this point, this is equal to Sn, right? If you look at what this is going to be when we evaluate it, we see that it's exactly the sum of these terms. So that's great. So we can say, because of our assumption, we can say that Sn plus 1 is equal to Sn plus 2n plus 1. And by our assumption, this is equal to n squared plus 2n plus 1. And then we can actually just go directly to what we wanted to show. Okay, if we expand this, then we're going to get exactly n squared plus 2n plus 1. You can check that if you want to expand it yourself, but this is the factorization of that. And so we've shown our claim. Our claim was right here, and we've shown that. Yeah, so we give ourselves a big tick. And we've in fact shown that given our assumption, in the case that n is equal to this big N, we've shown that that implies it's true for Sn plus 1. So if we go back to our idea about induction, we can now say it was true for n is 1 because we checked that. And so by our inductive hypothesis and applying this inductive step, we can say it's true for n is 2, it's true for n is 3, and in fact it's true for any n. So this is kind of cool. So what we've shown is, so the sum of the first n odd numbers is what? Well, it's equal to n squared, so it is the nth square number. Okay, cool. So that's kind of random, right? I don't think we would expect that straight off the bat. So maybe I can give you some intuition as to why that's true. This is quite a cool picture. So there's 1 dot, that's 1 squared, which is 1. Let's add the next odd number, which is 3. Now we've got 4 dots, right? Now we add 5 dots, that's 3, 4, 5. Now we've got 3 squared, which is 9, right? And you see where this is going? We just keep adding the next odd number. We just added 7 there. Now we've got 4 squared, yeah? And so this is the idea that we can carry on going like this, and we're just going to keep getting a bigger and bigger square each time. And so there's maybe some intuition behind why that's true. Okay, cool. Hopefully that was useful. And yeah, I look forward to doing my next video.